The last question we had was on 2374. 2374 says we can start with a product that or a reactant that looks like this, treat it with acid, and end up with a product that has a formula C15H12. It also notes that its spectrum is mostly aromatic, except for one alkyl peak. So everything's going to be aromatic except for one peak. The easiest way for me to think about this is to think about what actually is going to happen in this mechanism. We have an HA, an acid, just a generic acid, it doesn't matter what it is. We want to think about where is the most likely place that that acid will bind onto. What is going to have the most basic set of electrons? It's not generally going to be these aromatic rings themselves. It's actually going to be one of the lone pairs that's on this carbonyl. And so the first thing that we're going to do is bind an H plus onto this location. When we do that, I'm going to draw this relatively small, but we end up with something that looks like this as one of our resonance structures. Of course, we can also have this stabilized as the carbonyl. This is relatively positive and can now react fairly easily with another aromatic through a nucleophilic aromatic substitution. And so that's what we'd expect to see. When we do that, we end up having this positive react with this group, because this is going to be the only way that we can form a six-membered ring with the types of sterics that we see. So we'd expect these electrons to kick out and join here, and then we would expect to eventually use whatever base was eliminated from this acid as a local base to restore the aromaticity at this point. So we'll end up with an intermediate that looks like this. Now we still have acid present in solution, and we don't have full aromaticity yet, and our formula doesn't match up with this. If we actually counted out all the H's, we'd have an extra water, which suggests to us a dehydration. No surprise, this will pick up an H+, and we can eliminate using really the only acidic hydrogen that's available here. So this will leave as water. It'll create a positive charge here that's aromatically stabilized, and we can use whatever base is present in a separate step to then drive us into the alkene. So our final product is going to look like this. We can tell for sure that it's aromatic, actually not because we have distinct aromatic rings, but because all the way around the outside of the ring we have 2, 4, 6, 8, 10, 12, 14 electrons, which follows the Huckel rule for aromaticity. This is an aromatic compound, and this is our single peak that's outside, coming from this carbon up here on the starting material.